Okay, everyone, this is Dr. Ripley here, and we're going to do something really important right now. We are going to look at how we can take the things that we've learned so far about how probability works for model devices like dice, and we can use it to learn things interesting that represent actual biology, because this is a statistics in the life sciences class. And so my question is, how can dice equal ducks? And that is what we're going to look at. All right. The way that we're going to make this happen is that we're going to take whatever we're biologically interested in, and we're going to define a variable that's the numerical outcome of a random phenomenon. All right. That sounds really vague and obscure, but basically we're going to say we took a random sample of ducks, say, all right? We went out into a marsh and we looked at the nests of these ducks, all right? So that was a random sample. So that's going to be the result of a random phenomenon. And what did we do? We measured something about the ducks. We could have measured the weight of the ducks. We could have measured the number of eggs that are in the duck's nest. Okay, so something that we measured that we think of as a normal biological variable, and because we took a random sample, it's going to act like the result of any random process, right? So we're just going to denote it X or Y. We're going to say, hey, my thing that I measured, my biological variable that is really a fascinating thing, we're going to make it sound really boring and abstract by just calling it X or Y. Okay, so we can do this for a continuous variable. It could be the mean of our random sample. We can do it for a discrete variable. It can be things like the sum of the rolls of two dice, right? If we roll two dice, we have two numbers. What do we do with it? How do we make it into a random variable? We add the numbers together. All right, so we rolled a one and a three. A random variable is the sum. All right, if we're looking at numbers of children in families and which ones are boys and which ones are girls, then we can say, oh, here's a family of three children. How many out of those are boys? One, right? Okay, it could be zero, right? So we're going to just make, it's a little trickier to think about it for a discrete variable, but we are going to make something biologically interesting into a random variable. And we're going to focus on discrete random variables. Discrete random variables just means that they are ones that have categorical outcomes. So just like we've been looking at different dice with different sides or different possible things that can happen, how many chips did we pull out of a bin that are one color versus another color? We're going to keep using that exact same scenario. So there's going to be some possible values that our outcome can have. We're not going to call it heads or tails. We're going to have to name it number of heads out of three coin tosses. Okay, so we have to convert it into something that matches this pattern. Um, so whatever the possible outcomes are, they may start at zero, they may not. We're going to write those down. What are all the possible? What's the sample space, right? And then the probability of each of those different things happening. So to get it from a real biological entity, we'll actually have to go out and say, oh, look here, here's a nest with three eggs in it. Go and count a bunch more nests and then find the frequency of nests with three eggs out of your large sample. Right, so we're going to summarize that information by making a little data table with the value of our variable and then the probability of getting that particular outcome. So we'll call this a probability distribution table, and we can turn it into a probability distribution graph or sketch of the graph very easily. We've already been doing this. All right, now a cool thing we can do when we have turned a categorical outcomes into a discrete random variable is that we can we can find a mean and a standard deviation of the distributions. All right, so this is kind of the situation that we've talked about already, where we might take the mean of something and find we can't actually end up with it of that value. We can't have 3.5 duck eggs, right? But across the whole population, that isn't a useful piece of information. All right, so our mean mu of our discrete random variable, we're going to calculate it by taking the sum of each of the value of the possible outcomes multiplied by its probability. So this is actually, sometimes you might hear this referred to as a weighted average. We don't have each of the actual outcomes. We've already converted it into a probability. So we just are going to multiply the probability times the value of the outcome, and then add those up for however many possible outcomes we have. A standard deviation, we're going to calculate it from the variance. The variance, we're going to write sigma squared. So we're going to take this quantity, and then to find the standard deviation, we'll just take the square root of it. All right, so just like our standard deviation for quantitative variable, we're going to take each individual value of the outcome. We're going to subtract the mean, right? So we have to calculate the mean first before we do the standard deviation. We're going to subtract the mean. We're going to square that quantity. And then just like when we calculate the mean, we're going to multiply it times the probability of getting that outcome. All right, this notation may look a little confusing to you, but I'll work through some examples so that it makes plenty of sense. All right, we're going to start with a familiar scenario so we can see how it translates into this new notation and this new way of thinking that we are looking at this idea of a random variable. So we're going to say flip a coin 2 times, and we're going to count the number of tails. All right, so our random variable, capital X, is going to be the number of tails out of our 2 flips. And we're going to assume that we have a fair coin. The probability of heads equals the probability of tails, and that equals 0.5. All right, so we've assigned our probabilities, and we're going to write our sample space. We're going to flip a coin 2 times. All right, so our sample space, what are the things that can happen if we flip a coin 2 times? Well, professor, we can get a head and a head. We can get a head and a tail. We can get a tail and then a head. We can get a tail and a tail. All right, so in terms of our random variable, we want to convert these different possible outcomes in our sample space. We want to convert them into our random variable. All right, so for our random variable x, if we get 2 heads, how many tails do we get? Well, professor, that is 0. All right. And if we get 1 head and 1 tail, we're going to get 1 tail. Or we can get 1 tail if we get a tail then a head. All right, so we're converting our sample space from our scenario into our random variable. We can get no tails, we can get 1 tail this way, we can get 1 tail that way, or we can get 2 tails. All right, so there's 3 possible outcomes for our random variable. So we're going to draw our random variable distribution table. We want to write the x, what's the value? I'm giving myself lots of room so I can add up the probabilities here. And then what's the probability of x? So we're going to find the probabilities of x just like we've been doing to practice. If we have 1 head and then another head, we're going to take the probability of getting a head times the probability of getting a head again. Sorry about that. So that'll equal 0.25. We're getting a 1 for our random variable. We're going to have to take the probability getting of head tail, which is going to be the probability of getting ahead times the probability of getting ahead. Sorry, head and then tail, plus probability of getting tail, and then ahead. It works out to be the same thing because this is a super boring example, professor. All right, so we've done this a bunch of times. It should be familiar. You should be following along. All right, here we go. So this is going to be 0.5. And then the probability of getting 2 for our random variable number of tails is probability getting a tail and getting another tail. So we're also going to do 0.5 times 0.5 equals 2.5. All right, so we convert just flipping 2 coins into a random variable. We're saying, okay, we want a numerical outcome of this. How many? Right? We could say how many heads do we get, or how many tails we get. Probabilities are equal, then we're going to get the same numbers. But this step is really important of thinking through how you're going to convert whatever's happening in your sample space into tallying up or calculating the probabilities of getting the outcome of what you're interested in. All right, so we can sketch our nice little probability distribution graph. The name of our random variable goes on our x-axis. It has 3 possible outcomes, 0, 1, and 2. Those will be our tick marks. We've got the probability on the y-axis, and we only have 2 values, 0.5 and 0.25. All right, so we're going to draw bars, and they are separate from one another with spaces because it is a discrete or categorical variable we have on the x-axis. All right, let's calculate the mean of our discrete probability distribution. So the equation for that is that mu is going to equal the sum of our values of x sub I times probability of our x sub I. Right? What are our x sub i's? Those are these values here. So we've got 0, 1, and 2. We're going to have 0 times its probability. We're going to add, so that's the first term. We've got all the information we need right here in our little table. We're going to have 1 times 0.5, and we're going to add 2 times 0.25. All right, that's going to be 0. That's 0.5. That is going to be 0.5. Oh, look, it's going to add up to 1. All right, and that's what it should. Look at our distribution. All right, it should, that makes sense. Okay. All right, that is how you apply this equation to your actual data. Right, it's all here right in the table. Now we're going to start with the variance on our way to calculating the standard distribution as well. And that is going to be the sum of each individual outcome minus the mu squared times the probability of that outcome. All right, so again, we're going to have 3 terms. We've got our mu here. So we're going to have 0 minus 1 squared times its probability. And we're going to add 1 minus 1 squared times its probability, 0.5. And we're going to add 2 minus 1 squared times its probability 0.25. All right, so 0 minus 1 is minus 1. We're going to square it. We're going to get 1 times 0.25. So that's going to equal 0.25. Well, minus 1 is 0. So multiply times 0.25, that's going to equal 0. And we're going to get 2 minus 1 is 1 squared times 0.25 is 0.25. So our variance is 0.5. Our standard deviation is the square root of the variance. So we're going to take the square root of 0.5, and that is 0.7. All right, so that's going to give us the standard deviation, and that also makes sense. All right, so this is an example of how we can turn a sample space into a random variable and the steps of how to calculate an example of finding the mean and the standard deviation of our discrete random variable. Do you completely get that? Possibly not. Let's look at another example. All right, let's make it a biology one. All right, suppose I have gone out and I've looked at those ducks, and ducks lay a lot of eggs at once, and they can actually, females can lay different numbers of eggs depending on how much, basically how fat they are as they get ready to lay their eggs, how much stored resource they have. All right, so we went around in this swamp, we found all of these duck's nests, we counted up the number of eggs, so our variable x is the number of eggs in a duck's nest. All right, and we found between 3 and 6. All right, so there was not a single nest that had 7 or more or 2 or less eggs in it. And after we counted all of those numbers, we divided by the total number of nests, we scratched our mosquito bites, and we found that we had 3.5 that had 3 eggs in the nest, 0.45 that had 4 eggs in the nest, 0.16 that had 5 eggs in the nest, and 0.04, not that many, had 6 eggs. All right, so these values for our distribution, we had to empirically measure. All right, from a large sample. All right, let's sketch our discrete probability distribution. And we're going to have values on our x-axis for the different possible outcomes, 3, 4, 5, 6. The variable name is number of eggs. Our probabilities range from 0.04 to 0.45. I'm going to do 0.5 and 0.25 because this is a sketch. We don't need to kill ourselves trying to make it perfect. All right, we're getting our discrete bars here for each. Oops, I missed that one. Right, as you can see, I'm not making a perfect sketch, but you can get the idea of the proportions of different nests with different amounts of eggs in them easily from this little sketch. All right, it's a sketch, it's not perfect. And this one is small. It's probably even too large, right? It's not so easy by eyeball to figure out what the mean and standard deviation of this distribution is going to look like. All right, once we have data like this, though, suppose these are ducks that are being managed for hunting, and we want to maintain a certain population size of ducks. We want to check that the number of duck permits that are being granted every year is going to be replaced by the proportion of eggs that are being laid. right? So we might want to calculate some different things about this population. We know, we might want to know what the probabilities of different things are. So like any of our events in our calculations with probability, we could say, what's the probability that x equals 4? That is, what's the probability that ducks lay exactly 4 eggs in their nest? And we just read that off the table, 0.45. Going to ask a question of what's the probability that x is greater than equal to 4? All right, greater than or equal to, I'm going to include the 4 and everything larger. So I'm going to add the probabilities of 0.45 plus 0.16 plus 0.04. All right, and that's going to give me 0.656. Okay. We can also do things like the probability that x is not equal to 3. All right, now we could add up all of the ones like we just did. All right, so probability greater than or equal to 4 is actually equal to probability x does not equal 3. All right, or we can use the rule that these all have to add up to 1, and we can say, well, we've got 1.0 minus 0.35, and that's the probability of getting a 3. So not getting a 3, 3 eggs in a nest, is going to equal 0.65. So let's do so sub x sub or different possible x sub i's. X y probability x y. So variable names capital X. These actual numbers are the little x, 3, x 4, etc. So times 5 plus 4 times 5 plus 5 times 6 plus 6 times 0.4. We're going to add those up and get 3.89. Check on your graph and see if that makes sense. All right, in case you made a mistake in this calculation, if you got 7.5, you would know that you had made a mistake somewhere and could go back and check your work. All right, yeah, that makes sense. It should be around 4. Oh, sorry. All right, now we have mu. I'm round, oh, no, I didn't round it off. Okay, so the variance, sigma squared, is going to be the sum of our x sub I minus mu's squared times probabilities of each of the x sub I. And so our mu is 3.89. That's going to equal, I'm going to put a big bracket around it to start out. 3, first value, minus mu minus 3.89 squared times its probability, 0.35. And we're going to add our next one, 4 minus mu, square that term, multiply times its probability, 0.45, add 5 minus also the mu. Oops, I wrote that wrong. Square that, multiply it times its probability, 0.16. All right, notice something I'm doing on my paper, just the way I write out the terms helps me make sure that I wrote them all. I like to do this better than usually writing them out kind of all along the paper. Whatever works for you, keep it organized and make sure you're going through it systematically is just fine. All right, so first I'm going to do these subtractions, then I'm going to square those terms, then I'm going to multiply. All right, and when you add it all up, you should get sigma squared equals 0.657. And we're not done because we want sigma, standard deviation. We're going to square the sigma square. So 667, and that equals 0.1 standard deviation. Not super excited to have found this, but this is an important skill, making our way toward understanding all different kinds of ways that we can summarize distributions, finding the means and standard deviations. And this concept of this weighted mean is can be quite helpful. The last one, I'm going to give you the problem, and then I'm going to ask you to work it out yourself so that you can make sure that you're understanding how to do this. And but I'll write out the answers for you to make sure. So we're going to have a bag with colored plastic chips. All right, so we're going to pick 3 chips. And we're going to tally up the number yellow. So what is our variable? X is going to be the number of yellow chips out of 3. And I need to give you the number of draws. Okay, so I'm going to write the table vertically just to help keep you on your toes, flexible. We can do this. Sometimes if it's a little longer, just if we prefer to write it this way. So you're going to have a possibility of having, we're pulling 3 chips. You could have 0 yellows, you could have 1, you could have 2, you could have 3. And the number that I actually drew, I'm going to tell you, 0, 4, 12, and 4. All right, so first we want to add up how many there are. So what's our sample size? And equals. And then you're going to use that to find the probabilities. So what's my probability? X. You're going to calculate that one's going to be 0. But how do I get there? This is 20 total. So this is my 0 divided by 20. All right, so start by filling in the rest of the probabilities here. Sketch me a probability distribution. And then find the mean and the standard deviation. All right, so I'm going to be able to figure out from the mean of this distribution what the proportion of yellow chips is in out of that. All right, curious, all the rest of the chips were blue. We're only looking at the yellows. Okay, make that calculation on your own and come back in a minute to check if you got it right. And I'll work out the steps here. Just turn off your video and come back to it to check on your own work. All right, did you get it? The mean is 2.0 and the standard deviation is 0.63. All right, so we can estimate that 2 out of every 3 chips, or 2/3 of the chips in the bin are yellow, and the other third is blue. Woohoo! We can use this for much more exciting things. All right, thanks for following along today. I hope this helped you learn, and I will see you soon.